So by doing this, we transferred this scene into some tabular data. So we've gone through the last few classes analyzing this tabular data. The last thing that we did was I gave you some additional data. I said, okay, what if we have some instantaneous rate data? So at these different time points, when the concentrations of A and B are different, I gave you these instantaneous rates. So just to be clear, I made up this data to be convenient for us for class. Okay? So I'm telling you, we have this information, and what I posed to you last time was, if we have that information, can we now determine the full rate law? And yes, we can. So we started on last time, and we were kind of rushing towards the end, so I want to start with this question again. So we have this data, and our question or our task is we want to determine our full differential rate law. Okay. And everybody can hear me okay, right? Does anybody have a problem hearing me in the back of the balcony? Okay. So what do you think the first step is that we're going to do here? We want to try and determine the full rate law, differential rate law. The super basic first step that we're going to do. Yes. So let's start with the most basic. Let's pose a possible rate law. Okay? So let's pose this in. We have a reaction going A to B. And let's pose this simplistically, just thinking about the rate of the reaction with respect to the reactant A. So rate with respect to A. Now, A is a reactant, so remember we're talking about our differential rate law. So the derivative of A with respect to T is equal to negative rate constant times A to the X. Okay, so we have here our form, we're thinking about it just in terms of the reactant here. And we have a rate constant that we have to figure out, and we have to figure out the order with respect to A, which also happens to be the overall order since we only have a reactant in this rate law. Okay, so we have a possible differential rate law. Now what's the next step you think we're going to do? Which one do you think we'll go after first? The rate constant or the rate of your order? Order. So first thing we want to do is let's find the order. Okay. So how are we going to do that using this data? I'm not afraid of silence. Come on. Well, let's not talk about the answer, let's talk about the methodology. Sorry?
One reactant going one product.
So we have one reactor going to one product. But remember, I'm glad that you said that. Remember that when we have these reactions, unless I tell you specifically that this is an elementary reaction, you can't make any assumptions about the order from the stoichiometry here or the reaction.
So we're finding the order with respect to A, and the concentration of in A is halved from T0 to T1, and the rate also goes down by half, so it's first order.
Right. So let's walk that through and make it clear for everybody. So what we want to do is compare data points here. What we're looking for is some place that A is changing and we have a change in rate. So in this case, any two of these points would work. So let's compare say, the first two reactions, or the first two data points. Okay? So let's talk about 0 and time 7.5 seconds. So we can actually look at that as we said so. Let's just write it out. We had at the 0 time point, 1.5 molar per second is equal to K times 16 molar to the x, and 0.75 molar per second is equal to K times 8 molar to the x. Okay. So a couple points here that so it doesn't get confusing throughout the class. If you notice in this table, because I'll show you another table, I listed it as negative, EAGT, so they're already positive. That's why here I'm not including the negative sign there, because I've already taken it down to the data. So we can do this sort of intuitively, just looking at this, and say, okay, well, if we increase the concentration, or we double it, we get a doubling of our rate. So if we double the concentration, we double the rate. That seems to indicate that it's first order. So we can do that intuitively, but we can also do that looking at actually numerically with the rates. So what we said last time that we can do is we can actually divide the two equations. So if you want to be absolutely sure, we can now divide the left and the right sides. So 1.5 molar per second over 0.5 molar per second is equal to K times 16 molar to the x over K times 8 molar to the x. Conveniently, our rate constants cancel. So now we have 2.0 is equal to, well, now we've got numerator and denominator raised to the same power, so we can bring them in together. So we have 16 molar over 8 molar to the x, which is equal to 2 to the x. And so that means that x is equal to 1, or as we said, it's a first order reaction in A and overall. So we can now start to fill in information with our differential rate law. Given this, we now know that the derivative of concentration of A with respect to time is equal to negative K times A to the first power. So our next step then is to solve for K, our rate constant. So how are we going to do that?
Plug in values for A over dt and the concentration of A and solve for it.
Yeah, so we're going to plug in, we are just going to pick, to start off with, we're just going to pick one of these points. We've got concentrations of A with their matching rates. So we can use any of those points. Let's start with the first one again. So we say we now want to find the rate constant. We want to plug in our data. So in this case, we can say 1.5 molar per second, K times 16 molar to the first power. If we go ahead and do that math, then we get 0.094 1 over seconds is equal to K. So in practice, say you were doing this in lab and you wanted to come up with this value of K, what you would do is more likely you would find K for each of these pairs and then take the average as your average value for the rate constant. In this case, we're not going to do it because I don't want to go through that exercise for a full day. But that means that now we have our full differential rate law. So the derivative of A with respect to t is equal to negative 0.094 1 over a second times concentration of A to the first power. Okay, So with the differential rate law, what this form of the rate law allows us to do is say, at given concentrations, how fast will the reaction go? But now let's think about a different question that we might want to ask with this reaction. So we're not going to need that data for right now, so I'm going to get that away over here. So let's pose a different question. Let's suppose you're a home brewer of beer. Okay, so you make your own beer in your closet at home, whether or not you're 21, I don't know. But let's say that you use compound A at 10 molar to give your beer a unique flavor. The problem is, A itself is toxic to humans, but it does decay. So what you want to figure out is, can I keep on using A to flavor my beer, or do I have to worry about killing people if I feed them this beer that's not tasty? Okay, so maybe I've been doing this a while and I'm not really sure whether maybe I just built up some immunity to it. So let's think about this question. So suppose we group here and use A and 10 molar flavors. Okay? And you're adding A right at the beginning of the fermentation process. But A itself is toxic with a lethal dose of 50% of 0.25 micromolar, which is the same as 2.5 times 10 to the negative 7 molar. Okay, so lethal dose 50. So this is the concentration of your compound at which you kill off 50% of your test elements. Okay, so if we feed animals with a solution that's about 0.25 micromolar, half of them are going to die. Okay, so obviously we want to be below this. So our question here is, do I have to worry about killer beer? Okay. So, of course, I'm trying to put this in some sort of other real-world context. We want to repose that question so that it's amenable to quantitative analysis. Okay, so do I have to worry about killer beer? And I know a lethal dose concentration. So let's rephrase that. Suppose that means that my safe and acceptable concentration is the LD 50 over 1,000. So as long as I'm 1,000-fold below my LD 50, I'm okay giving this beer to my friends. I'm not going to worry that I'm going to just have a massacre at my next party. Okay? So that's what we're saying. Okay, we need to get our compound A, flavor compound A that happens to be toxic, below this LD50. So our question is, how long, or the time, to reach this safe level, or the concentration at that particular time? Okay, so this is becoming a question of, we want to think about concentration as a function of time. But our differential rate law gives us the rate as a function of concentration. So turn this rate law into a rate law where we have concentration of A as a function of time, and so we're going to have to transform it to an integrated rate law. So our integrated rate law will be concentration as a function of time. So at this point, I know some of you have already taken calculus or are taking calculus, but I'm not sure where everybody is, so I want to do a brief math review to make everything clear here. So let's remember our exponentials. So we have a to the x times a to the y. That's a to the x plus y for our exponents. And vice versa, the natural logarithm of x, or natural log plus the natural logarithm of y, is the natural logarithm of x times y. But then some of our calculus that we need here. So let's talk about derivatives. So if you have the derivative with respect to x of a constant, that's equal to 0. If you have the derivative of x raised to the power n, that's n times x to the n minus 1. If you have the derivative with respect to x, the natural log of x, that's equal to 1 over x. If you have the derivative with respect to x of a constant times a function of x, that's equal to the constant times the derivative of with respect to x of the function. So we can pull constants outside of the derivative. So we can contrast these to our antiderivatives, our integrals. So we have the integral of the differential of x. That's equal to x plus some constant. Remember, when we have antiderivatives, the solution contains the constant because the derivative of a constant is 0. So if you're going backwards, you get rid of this. So when we go from the derivative to the antiderivative, we need to add it in. We have the integral of x to the n minus 1, that's 1 over n times x to the n plus constant. Remember, we can check this going backwards, so if we take the derivative of this side, we use this rule, n times 1 over n is 1. And we decrease the power that becomes x to the n minus 1, and we lose the constant, except when n is equal to 0. In that case, we have the integral of 1 over x is equal to the natural log of x plus a constant. And finally, just like with our derivative, we have the integral of a constant times a function of x with respect to x. That's the constant times the integral of the function with respect to x. Okay? So we have just some of the rules that we can use here as we continue on figuring out our integrated rate law for this example. So that'll be up there as well. So let's come back to our problem. What we're trying to do is we're figuring out, okay, we have a given concentration of our toxic compound A that flavors our beer. We want to figure out when it's going to get below our safe acceptable limit. So this means that we have to figure out our integrated rate law. So find our integrated rate law. Well, we start with our differential rate law. So derivative of A with respect to t is equal to negative our rate constant times A. So A with A and get T to the other side. So we just cross multiply. So we have 1 over concentration of A times the differential concentration of A times negative K T. So now we're in a form where we can integrate both sides because we split up our variables. So we take the integral 1 over A dA times the integral 1 minus K dt. So now we're in our integration step. Well, now we can look at our rules here. So we know that on the left side, the integral of 1 over A dA, we said that that should be the natural log of A plus a constant. And we know on the right side, well, K, that is our rate constant, so it's a constant, and so is -1, so we can pull that out. So we're going to end up with the integral of dt. So let's write that explicitly, so we can say that that's equal to putting everything in the form of our map gt, negative k, integral dt. We can now say that that's the natural log of a plus a constant times negative k times t plus a constant. But we haven't figured out our constants, so it doesn't really matter that we treat them separately, so let's just move them together so that we can have a simpler equation. So bring that over there. We can say the natural log, the concentration of A is equal to negative k times t plus some constant. But we want to figure out what the constant is. We can do this generally because we know, in this case, being given, and usually you're given an initial concentration. So let's say that time equals 0. We know that our concentration is equal to the initial concentration. That's kind of a truth, right? So at time 0, the initial concentration of A is the initial concentration. So we can plug that into our equation. We now can say the natural log of A, the initial concentration of A is equal to negative k times 0 plus constant. So our constant is the natural log of our initial value of A. So that means that our integrated rate law is the natural log of our concentration of A equal to negative our rate constant times time plus the natural log of our initial concentration.
When you move the constant to the other side,
Yeah.
so subtract the constant, right?
Sorry, so I didn't write that. There are two different constants. So you're not canceling them, so let me say
Oh, okay.
constant 1, constant 2, so that's the constant 3. Basically, you don't cancel out the constants, but you still have to take into account that there's a constant. Okay, so I like to remember that you can use algebra now to put this in different forms. So one of the things I like to do is also move the logs over to the same side. The natural log of A minus the natural log of the initial value of A is equal to negative kt, because this, we can now combine these logs. So we have natural log of A over the initial value of A equal to negative kt. So why do I like that? Because it makes things a little bit easier here, because when I put it in this form, I'm not dealing with some weird natural log of molar. Okay, because I have the division of 2 concentrations, so I've gotten rid of my units, and now the natural log is much more comfortable for me. The other thing is that now I can think about changes in terms of fractional left or percent left. Okay, because I'm thinking about it, the amount that I have of reactants and the amount I start. Okay, so let's now put this back in the context of our beer problem. So in our problem, Well, we calculated from that data that our rate constant was 0.941 over seconds. Okay, that was from when we worked up the tabular. I said that we want to use this flavor compound initially at a concentration of 10 molar to get the flavor into the beer. So our initial concentration is 10 molar. And what I'm asking is how long does it take to get to 1,000 less, or 1,000-fold less than that LD50? So I'm trying to figure out this time that I hit a concentration of LD50 divided by 1,000, which is 2.5 times 10 to the negative 10 molar. Right, because we said that our LD50 was 2.5 times 10 to the negative 7 molar. So if I divide it by 10 to the 3, I get 2.5 times 10 to the negative 10 molar. So how long does it take for me to get to this safe, acceptable level? Now it's a question of just plugging this data into our integrated rate law. So let's do that. So we have 2.5, the natural log of 2.5 times 10 to the negative 10th molar over 10 molar is equal to negative 0.094 1 over second times time. And now it's a question of using your calculator. So this works out to be about 260 seconds is your time, which is about 4.3 minutes. Now, given that you're going to be fermenting and brewing your beer on the order of days, are we going to be worried about killing off all our friends when we serve our beer to them? No. Okay. So this is supposed to be an example of how you might go between the differential rate law and the integrated rate law. So let's just review now our integrated rate laws. I'm not going to drive all the rate laws for you. I highly suggest that if you haven't gone through it before, you go through the integration and work through starting from the differential rate law for the first and second order reactions and finding your integrated rate law rather than just relying on your book to tell you what it is. It makes it a lot easier to really understand where that comes from if you forget something that you try to memorize for an exam. But for now, let's compare them. So if we have 0 order, first order, and second order. That means our differential rate laws are negative K, concentration of A to the 0. Derivative with respect to A is equal to negative K, concentration of A to the first. The derivative of A with respect to T is equal to negative A times concentration of A squared. Then we can go through those same steps that we did with the first order reaction, figure out our integrated rate laws. So in this case, that means that for the 0 order, concentration of A is equal to negative KT plus the initial concentration for a 0 order reaction. For a first order reaction, the natural log of A is equal to negative KT plus the natural log of the initial concentration. That was the one that we worked out just now for the beer example. And for the second order, we find that negative 1 over the concentration of A is equal to negative KT minus 1 over the initial value of A, which we have negatives everywhere there, so we can just turn it into all positives if we want to. So we have relationships between our differential rate laws and our integrated rate laws. But the thing that you want to notice here is the form that the integrated rate laws take for these 0, first, and second order fundamental reactions. These are all now linearized. So that means that we can figure out order and eventually rate constant without knowing rate data. And the question, of course, now is how. Well, look, the first step we did after we wrote the equation for our rate law was to try and figure out order. That's the key here, is now we have a method using the convenience of these forms to figure out the order without actually having rate data. So what we're going to do is we're going to look for linear plots. So if you look at this, if we plot these different things, we have y, slope times x plus intercept. Okay? So y is equal to mx plus intercept. Y is equal to mx plus intercept. Y is equal to mx plus intercept. So if we plot concentration versus time, that's linear. That means it's zero order. And that means that our rate constant, we can figure out that the slope is equal to negative k. If we plot natural log of a versus time, that's linear. That means it's first order. And the slope is equal to negative k. If we plot 1 over a versus time, and that's linear, that means it's second order. And our slope, in this case, because remember, our negatives all canceled out, our slope is positive k. So we can actually see this. So suppose I didn't actually give you this data for figure 16.1, and I only left you with the concentration. Yeah. Can you move the sheet up a little bit? Oh yeah, sorry. So if I have these concentrations of A, but I didn't have the rate data, what I could do is calculate, let's just figure out what's the natural log of A, what's 1 over A at these different times, and plot the graphs. So if we do that, here you can see that there's a linear plot when we have natural log of A. And we've said that if natural log of A versus time is linear, that's first order, and the slope is negative k. Our slope is negative 0.092. So our k from this data would be 0.092, which is pretty close to what we figured out in a different method, 0.094. So our integrated rate law gives us another method by which we can come to a full description of our rate laws, either differential or integrated. So once we have the order, remember, we have order and we have other data points, now we can solve for the rate constant. And this is explained graphically in your book in figure 16.10. So this is more to review what's going on here. So who wants to see a demo with puppies?
Yes.
Do you really want to see a demo with puppies?
Yes.
Okay, really everybody wants to see a demo with puppies?
What happened to the puppies?
Like little puppies?
Are they here?
Okay, really? Really?
Yes.
Yeah, I don't have any puppies. No, I couldn't figure out a demo that really illustrates the integrated rate laws very well, so puppies. So instead, what we're going to do is we're going to talk about macrologs now. Okay? I know, isn't that a great segue? Okay, let's talk about
Is it new? There was no rings. Yeah.
So, the other thing that integrated rate laws allow us to do is think about, as we actually did with our beer example, what we had, the knowledge we had was we had a certain concentration, and we had to figure out how long it would take to decay the reactant we consume until you get to that concentration. Well, that's a more general case when we're thinking about half-lives. When we talk about half-lives, we're asking how long does it take for our initial concentration to decrease by half? Okay, so it's actually a much more special case of what we already did. But we can think about that in terms of our integrated rate laws. Okay, so this is the time T1 half when our concentration is equal to 1/2 of our initial concentration. Okay, nothing so groundbreaking there in that definition. But what we want to do in this case that we already did for our beer example, but now for half the initial concentration, is we want to solve our integrated rate law. So you can do this by plugging in 1/2 the initial into our different integrated rate laws. I'm not going to do that there because it's algebra and it's in your book, and you should practice doing it so you understand where these half-life equations come from. I'm not such a fan, which is why I went through the derivation of the integrated rate law of you just memorizing the equations. I think it's a good idea for you to understand where they come from, so in case you forget what the equation is, you can just derive it, all starting from being able to write that differential rate law. Okay, then the only thing you have to remember is how do I write that differential rate law. But in this case, let's just write down what we've got. So our zero order, our first order, and our second order. So for our zero order, when we solve that, T1/2 is equal to our initial concentration divided by 2 divided by our rate constant. For our first order, T1/2 is equal to the natural log of 2 over our rate constant. And for the second order, our half-life is 1 over the rate constant times the initial constant. Okay, so let's talk about these specific cases here. So, which of these is not like the other? So first order, why is the first order not like the zero order, the second order? Yeah.
Because it doesn't require the initial concentration.
Yeah, so we have no initial concentration term here. So the half-life is the same no matter how much you start with. So if I start with 10 molar and I know that the half-life is 5 years, it's going to take 5 years for 10 molar to go to 5 molar. If I start with 7 molar, it's going to take 10 years to go, did I say 10 years? Yeah. 10 years to go to 3.5 molar. Okay, so the time it takes to have your initial concentration doesn't change. Whereas for the zero order, the more you have, the longer your half-life is. So if you think about that, qualitatively, that means that as your reactant is consumed, your half-life is actually going to get so for the zero order, as you start consuming it, you think about what are your other half-lives as you go from 100% to 50%, and then 50% to 25%, and 25% to 12.5%. Your half-lives are going to get smaller because your initial concentration at that point is decreasing. Whereas for the second order, your half-life is actually going to get longer because your initial concentration is decreasing. If you think about snapshots in time, so the first half-life is going to be some value. The second decay from 50% to 25% is actually going to get longer. The special case here is that for first order, it doesn't matter what your concentration is. Okay, so that means that we can think about solving some of these half-life equations in two different ways. We can solve the actual integrated rate law, or we can think about how many half-lives have actually passed. So let's do an example. So let's say that we have a rate constant of 0.25 per second. And I want to figure out how long until only 6.25% of A remains. Okay, so we can do this two different ways. So first thing we can do is just figure out from our equation what our half-life is. So from our equation, we have natural log of 2 over our rate constant, 0.25, 1 over seconds, which is 2.8 seconds. Then, if we want to do this without solving our integrated rate law, what we can say is, how many half-lives until we get to 6.25%? So we start from 100%, we got decreased to 50%, decreased to 25%, decreased to 12.5%, decreased to 6.25%. Well, how many half-lives? So that's one half-life going from 150%, two half-lives going from 50% to 25%, three half-lives going from 25% to 12.5%, and another half-life going from 12.5 to 6.25%. So that's 4 half-lives. So we can say that time is going to take 4 times 2.8 seconds, which is 11 seconds. And so we can use our knowledge that it's a first-order reaction, thinking about our half-life without actually having to solve the integrated rate law. That's one way to do it. I actually personally find it easier to just solve the integrated rate law. And you should come up with the same answer. So let's do that. So our integrated rate law number is the natural log of concentration of A over the initial concentration of A equal to negative AT. Well, when we say 6.25%, that means that the fraction A over initial value A is 0.0625. So we can now plug in our values. The natural log of 0.0625 is equal to negative 0.251 over seconds this time. And if you actually solve this, you'll find that t is equal to 11 seconds. That it should be, because no matter how you solve it, you should come up with the same answer. Okay? So, if I gave you this information, and I said that there was a second order reaction, and I asked you how long would it take to get to 6.25%, what would you do? Yes, you would ask for the initial concentration, tell me that the question is incorrect. Right? Because we need, for a second order reaction, we need to know what our initial concentration is. So you can only do this exact type of analysis when you know that it's a first order decay. So that we can do similar type tricks for the zero and second order, but it ends up getting kind of confusing. So I would say, that's why you want to know how to do it both ways, with the integrated rate law and thinking about half-lives that have passed. Okay, so I think that we're going to start with collision models, phonetics, and elementary